So, warm welcome to this lecture. My name is Vikram Gadre. I am a professor of electrical engineering in the institute, and I work in the broad area of communication and signal processing. And my connection with linear algebra is that at one level, a lot of signal processing is linear algebra, or you could say put it the other way. A lot of linear algebra is signal processing, and that's also a view. Now, you see, the perspective that I'm going to take in this session is to look at certain system and signal ideas from a linear algebra perspective. And I'm going to follow certain practices of active learning. And the reason for doing that is not so much that you need the active learning, but more that you carry it also as a paradigm when you teach, because this is supposed to be a teacher's enrichment workshop. So it's not simply to enrich the concepts, it's also to enrich pedagogical practices or paradigms of teaching, right? So we will follow that. We will follow a certain way of exposing the subject with the intent that you can adapt it in the way that you find suitable when you deliver, content on this line. Now, we have first, in fact, I'm going to take maybe a slightly different perspective from how you would traditionally find transforms being presented. The subject I'm going to deal with is transforms. How many of you heard the word transforms? I think, there will be scarcely a person who has not. Isn't it? Can you raise your hands? Yeah, almost everybody's heard the word transforms. Well, I'm going to give you just half a minute. You can just recall which transforms you've heard about, right? And then you can take another half minute to talk to your neighbor, and then see if you can enrich further. You can expand. I'm going to pick on any group to share with us which transforms you're familiar with. Yeah. Take half a minute, or maybe take 15 seconds. Recall. Now we'll see. Now please follow the process properly. In the active learning process, now we need to do this practice properly. We need to do these processes properly. So don't compromise on their. The way we do it is, and this is, there's a formal thing called think, pair, share, but let's not worry about the terminology, or it's an adaptation. We adapt these active learning techniques when we teach, but here I'm following a version of think, pair, share, and what you do is the first step there is to spend the assigned time thinking. When you're spending the assigned time thinking, you don't talk to your neighbor, right? So you must follow that process properly. So you should not start talking to your neighbor in the think step simply because it destroys the purpose of the next step. Okay, so in the think step, you must first reflect on your own for whatever time you've been told, say 15 seconds, half a minute, 1 minute, 3 minutes. And then in the pair phase, in the next phase, you are required to, of course, discuss. In that time, you should not sit quiet. You should discuss with your neighbor. And then after the pair phase, then the share phase, we then have the whole class works as one. So and let's stick to the time. So we'll give you 15 seconds to think of transforms. In this phase, I should not hear a word being spoken by anybody. You write down on your notebook, write down the transforms with which you're familiar. And now we come to the pair phase. Now you can talk to your neighbor, not to anybody else. Neighbors, there are a few groups of 3 people. Now you can enrich your collection of transforms by talking to one another. And that you get only 10 or 15 seconds for that. Okay, now I would like to invite a couple of groups to share what they've come up with. So may I have any volunteers? So we'll have volunteers. Any volunteer groups? Any group would like to volunteer? Yes, very good. Yeah, why don't you come here?
Good morning.
Introduce yourselves and then share your.
I'm Dr. Sanjeev Ahuja. I'm teaching to the engineering students, and we both have discussed about the 4 transforms which we have learned, or maybe we have teach somewhere. One is the Laplace transform, might be you are aware of.
Yeah.
And Fourier transform is another one, and Z transform. One more I have not studied up to the mark, but I have listened. That is the Henkel transform.
Okay.
So these are the 4 transforms, and
excellent. Thank you, Dr. Ahuja. Very nice.
Thank you.
Yes, so you would like to share something more? Okay. But anyway, you can introduce yourself. No, the application right now is focus. Yeah.
So myself Raja, from PH Tech Coimbatore. So as he said, we discussed. all
Good.
those things.
Thank you. We'll have one more group, volunteer. Any other volunteer group? You'd like to volunteer? Please come. Yeah. You come. Introduce yourselves and share your. Thank you. Yeah, of course, you please do. Yes.
I'm Bhuma Devi from KC College of Engineering. That we have discussed about 4 transforms again. The first one, everybody knows that Laplace transform. The second one, Z transform, and the Fourier transform and wavelet transform. Then one more transform that I have come across in the when I was taking the NPTEL course, that is machine learning, Hausdorff transform, which is the identification. Through that transform, we can identify the figures, just like circles, wherever it is there, that we can find out that transform.
Very nice. Yeah. Anything else?
Good morning. I'm Swati Lavan. I'm working in Sardar Patel College. As she said, we discussed about Laplace, Fourier, etc. One more transform is wavelet transformation. And basically, these transforms are like transforming from, for example, from time domain to frequency domain. That is what the Fourier or Laplace transformation does. That is what I would like to add. Thank you.
Thank you. Now we'll just invite maybe one group or 2 groups if you have anything additional to what has been said. So now we, they put all, but would anybody like to add to what has been said?
Hello, I am Shilpa from Xavier's. I would like to add 2 more transforms that are conformal transformations and bilinear transformations that are coming under the area of complex
Conformal,
variables.
the other one was?
Bilinear transformations.
Bilinear. Okay. Very good. Yeah.
Myself, Sangeeta from Sardar Patel College of Engineering. As Madam has said, she is from mathematics and she is. I was not aware of these 2 transforms actually, linear and bilinear. Maybe we have used and the conformal. So that was a new thing for me also.
Anything? Anybody? One more group we can invite to add to what has been said. What has been said so far? Any other? Okay. So. Any other person keen to add?
Hello, I'm Pragati Gupta from VJTI, Electrical Engineering Department. We just want to add extension of Fourier transform, which is discrete Fourier transform. Why it came to our mind? Because when we are working with the PMUs and all, so for estimating phases, we are basically using DFT. So that's why that extension is just an extension of Fourier transform, like Z transform, which is a discretized form of, I don't know, Laplace or Fourier. I'm not very clear about that. Okay.
Good.
I'm Riza from St. Joseph's, and I think she covered it, and I came to know a lot of new things as well.
Good, good. Yeah.
Many new transforms we have come to know.
Very nice. Good. Thank you so much. Thank you. Thank you. Yeah. So, you see, you can see now, you can already see that there is such a rich collection of transforms that people know about. And in fact, this is just a small part of the repertoire of transforms that are used. And what we are now going to do is, you see, as I said, we're going to take a slightly different, maybe perspective from what might traditionally be done. Traditionally, we start with continuous time functions and we build transforms from them. In fact, Dr. Pragati Gupta, in fact, brought up the thought that one should also look at the possibility of discretizing, looking at discrete. So we're going to do that because when we actually try to apply transforms, it is easier to do them with discrete data. We are going to first work with discrete data, build a transform idea from there, and then go to the continuous domain. So I have 2 sessions and we are going to build that. Now, let's look at the whole idea of what. See, let's begin with a discrete sequence. So, how do you think of discrete data? Discrete data is really a mapping, isn't it? A discrete select. Now, you see, this is a maths enrichment workshop, so we should think. We don't want just to be informal in our presentation. There should be a little bit of formalism. So we'd like to look at it from that perspective. So, what is a discrete sequence? A discrete sequence is a mapping. It's a mapping from the set of integers, the set in general, the set of complex numbers. So this is, I'm sure many of you are familiar with this notation, isn't it? Anyway, those who are not. So this the script notation represents certain important sets. So script Z represents a set of integers and script C represents a set of complex numbers. So in general, a discrete sequence is a mapping from a set of integers to a set of complex numbers. What does that mean? Informally, it means that for every integer there is a complex number you have assigned. Now, why do I say complex number? Because in many engineering problems, we need to deal with so-called complex data. You may ask me, why should we deal with complex data? Complex numbers don't really occur in practice, right? You don't have 1 plus j, whatever, 1 plus j rupees, nobody wouldn't even accept such money. If somebody gave it to you, you might think it's counterfeit, isn't it? So the complex numbers don't really occur in practice. They are a convenient platform with which to work for real numbers, right? So complex numbers often become a vehicle to deal with real numbers. But then as a mathematician or as a person who teaches mathematics or mathematical subjects, we should respect complex numbers even more than real numbers because they have properties that go much beyond the real domain, right? So while we don't immediately see a practical occurrence of a complex number in the true sense, we do use complex numbers very effectively as a vehicle, right? That's why we allow, and of course the real numbers are a subfield of this, so there's no problem. When you say maps to complex numbers, the real numbers are included. The real sequence is also a part of this mapping. Now, we want to build this whole idea of transforms by thinking of systems on sequences. So let's take, in fact, now we'll do again a think, pair, share exercise, but this time it will be very quick. We'll only allow one group to share. Now, take only 5 to 10 seconds to think of examples of sequences that you encounter in practical life. Then take 5 to 10 seconds to share it. So let's begin the think part. Think of examples of sequences which you encounter in day-to-day life. I'll give you about 5 seconds. Think on your own. Then write down. The best thing to do when you think is to write down what you have thought. Okay, we'll have a couple of groups give examples. Any volunteers? I'd like to invite new volunteers if possible, but otherwise, yes, please. Yeah. Introduce yourselves.
I'm Dr. Narendra Kumar Dasare from RAIT. The sequences we normally use in daily life is Fibonacci sequence, very famous one.
Okay.
The integers, natural numbers we use mostly. And then in communication, we use binary sequences.
I'm Dr. Preetam Wani from RAIT. We'll discuss what he has shared.
Yeah, these are good examples, but there could be even more down-to-earth examples, isn't it? So any other, yeah, please. Yes.
So sensex values of the data is market
very good.
values, starting value of the market and ending value of the market.
Very good. Yeah, data, financial data can be an example of a sequence. Many of our students get very good jobs nowadays after doing discrete time processing because they deal with financial data effectively.
And if we are observing certain parameter, temperature, pressure at a particular time.
Yes.
After 1 hour, after 2 hours, all the data
very
are
correct.
discrete.
So, for example, if you look at the sequence of temperature values in a city over a year, daily temperature values or average temperature values over the day, or maybe the day and night time temperatures over, that could be an example of a sequence. Yes, very correct. Thank you so much. Good. We'll only have anybody add. If somebody would like to add any other example, if you would like to add, yeah, any other, so many others, isn't it? You could have, for example, you could have sequences that emerge from physiological processes. In a way, nowadays, a lot of recording, when people record electrocardiographic data, it is really a sequence. They don't record a continuous function. Nowadays, with digital machines, very often these are sequences that are recorded, not functions of time, not continuous functions of time. Right? So sequences, so we have so many different examples of sequences. Now, let's look at what a system means. So you see, you want to get information out of a sequence. So for example, you have digital cardiographic data, electrocardiographic data, or you have financial data, or might be you have data which has been collected about student performance, maybe over 10-15 years, spread over every semester, or maybe you have data collected about the population in different parts of the country or different parts, over maybe hundreds of years, whatever you have, and you wish to interpret that information. Interpretation of information requires processing, and processing is where the whole idea of transforms comes from. For example, all of you are familiar with audio compact discs, nowadays, or for that matter, audio files. Nowadays, whether or not you're an electrical engineer, whether or not you're a communication engineer, I think most of you must have played audio files, on a mobile. You might have played them even without realizing they are audio files. In the sense, you just click a button and you see a piece of music come out, right? That's really an audio file which you see on a mobile. Nowadays, people even play audio files on a mobile. Now, obviously, that audio file is not a continuous time function at all. The way it has been stored is a discrete sequence which is then played, right? So, in an audio file, what are you doing? You're recording the audio as a sequence of numbers, and then you're processing that sequence of numbers to generate back the audio that you hear. So, there are examples of sequences that you encounter right sitting here when you start tampering with your mobiles. Is that right? Now, in all this, you see there is a common thread. The thread is that the sequences by themselves are raw data which mean almost nothing. If I put before you the numbers of financial data, they tell you very little, right, as such. But you need to glean information from them. You need to make sense out of them. And making sense out of them requires you to deal with systems and transforms. So now let's look at both these ideas. First, let's talk about systems. So what is a system? You think of a system. Let's first talk about a discrete system. A discrete system is again a mapping. It's again a mapping. It's a mapping from sequences to sequences. Now, how will we denote a sequence? For example, we could denote a sequence like this. We use the square bracket to write the independent variable here. The independent variable is n, which is of course an integer, and x is the name of the sequence. So, x of n means for a given n, the value of the sequence x evaluated at the integer n, and when you think of n as a generic index for the script z, the set of integers, then you think of xn as an object, it's a sequence, right? The whole xn as a function of n in general is a sequence. For a particular value of n, xn is a value, right? But you can simply write x without putting the square bracket n, and that would imply this whole sequence, right? So, we are just getting our notation right. Now, in a system, we will prefer to use some standard notation. So, we will say x of n maps to the sequence y of n. Now, here you must be careful. You must not think of this as a mapping from x of n at a particular value of n to y of n at that particular value of n. No, that's not the way it should be. That's one possible system. It's a very restricted class of systems. But the most general class of systems treats xn together as a sequence for all n, and yn together as a sequence for all n, and then maps the sequence to the sequence. So, the system is a mapping above the sequence. The sequence itself is a mapping. A system is a mapping on mappings. Is that right? A system is a mapping on mappings. So, now building from there, let's take a couple of simple examples of systems that we encounter. Let's take the simple example of what we call an average, running average system. Is this visible at the back? Is everybody able to read what I am writing at all the corners? Yeah, at that corner and these corners. Yes? Is it visible clearly? I am writing large for that reason. So, let's take a running average example. We have y of n is half x of n plus x of n minus 1. Now let's understand, this is a way of writing down a system. So it's an example of a system, a very simple system. What does it do? It, at every point, at every value of the integer index n, you look at the current and the immediately past input sequence value and generate the output sequence by averaging them. Now, very simple to understand, there is no problem, right? What do you think could be the reasons for doing so? You want to remove unwanted fluctuations. I think the idea of averaging is known to all of us, right? That's nothing very complicated, it's not rocket science at all, right? So we understand what averaging does. Typically, there are different ways of interpreting what averaging does. One is that it gives you some so-called steady information that is present across the samples that are averaged, across the points of the sequence that are averaged. The other way of looking at it is that if there are small fluctuations which do not really mean much, they are removed if they are random, yes. The third interpretation can be that you wish to see what is slowly varying in the data as against fast varying. But now the third interpretation is something that we can only see with a little more work. We are going to do that work after a while. Now, let's look at this system from a slightly different perspective. So, we understand this system very well, right? The averaging system. In fact, you can have a more complicated average. This is a running average of 2 points, a 2-point average. You could have a running average of 3 points. So, you could have y of n is 1 by 3 times x of n plus x of n minus 1 and x of n minus 2. It's a running average of 3 points. And you could then generalize this. You could have a running average of n points. And of course, they would naturally have different properties. But now we wish to sort of quantify, or we wish to also characterize these properties in a different sense. To do that, let us now consider the example of an audio signal. Let's take the example of suppose you have a piece of music or a speech segment which has been recorded in an audio file, and it has been recorded as a sequence. Therefore, what you have done is you've taken an audio, somebody was saying something or somebody was rendering some piece of music, and it was recorded, and at different uniformly spaced points in time, the recorded electrical values are recorded as a sequence. That is a sequence that is called an audio sequence, right? So you have so if you had an audio sequence, or if you had, let's say, a speech, something that has been taken from a speech file, the sequence, what is the physical interpretation? The integer set here represents the sample number. So you have recorded a piece of audio. Maybe the recording is in the form of an electrical signal, so it would be recorded as an electrical signal. And then you can't possibly store a continuum of values. What you do is you look at this electrical signal at designated uniformly spaced points in time. Now, what would be typical values? What would be the typical separation? For speech, it is known that you don't need to sample more than 10 kilohertz. That means you don't need to sample more than 10,000 samples per second. In fact, 10,000 also is kind of, a little more liberal. You can probably do even with 8 kilohertz. And if it is audio, then you can do with about 40 kilohertz. That is 40,000 samples a second. That means your spacing needs to be, for speech, you're doing very well if the spacing between the samples is 1/10 of a millisecond. And on the other hand, for audio, you're doing rather well if your spacing is 1/40th of a millisecond, right? So, however, of course, that again is raw data. So, by itself, it doesn't make much sense. It would just be a sequence of numbers. But then you want to get something out of audio. So, for example, suppose you have a piece of audio in which there was both a group of male speakers and a group of female speakers. Or maybe, let us say audio. So, there were male singers and female singers. Both of them were singing together in a piece of music. How would you try, suppose you wanted to enhance the male voice and reduce the female voice, or vice versa. You wanted to enhance the female voice and produce the male voice in terms of intensity. What would you want to do? Now, typically, how does that translate in terms of the audio itself? What is it? So now again, now here I won't ask you. You can just respond. What would be how would you distinguish? What would be the feature to distinguish between male and female? Yes, the pitch. Now, how does the pitch reflect? What does the pitch mean? So the pitch. So yeah, can you elaborate a little? Suppose. So let me put it this way. Suppose it's easier to answer in terms of music. So suppose you had both of them sing a song together. What would be the difference? What would distinguish the male singers and the female singers? Yes? Amplitude? Well, yes. 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 Okay. Yes. Yeah. So I hear one response saying that the amplitude is different. And you're saying the pitch is different. Yes. What? Yeah. Any other responses? Yes. Yes. Yeah. Loudly.
It's mathematical perspective. Can we differentiate both the voice into different functions, x of n and y of n?
So I'll say don't think mathematically. Think of how a person would say play the music. From that point of view, can you? I mean, how many of you are musicians, or how many of you are? You are a musician? Oh, I see. So who is? Any musicians in this audience? Any? Shrillness. Yeah, that's interesting. Yeah, so it appears to be shrill. The female voice is more shrill. You're saying, yeah, okay. What does that really mean? So I told you music for a good reason. See, what you're saying for speech, that is more subtle. But for music, it's very clear. If the same song is being sung by a male singer and a female singer, in fact, when the male and female sing in a chorus, what distinguishes their singing? Can somebody throw some light? So let me first ask. So how many of you have some exposure to music? Can you raise your hands? Very good. You have some exposure to music. You also have some. You do too. Any others? Now can you then throw some light on that? So what distinguishes the male and female singer? If you think of a musical instrument, for example, what would you, in terms of the instrument, what would distinguish them? Yes. Can you pass the mic to him, please? Introduce yourself, and yes, please introduce.
I'm R.B. Gandhi.
Yes.
And I don't know what distinguishes between male and woman, but if a male sing in the voice of female, then he mostly uses nose.
Not necessarily, actually, not necessarily. Nasality is not necessarily what, yes, yeah. Yes, no, can you use the mic, please, because everybody can't hear you otherwise.
You asked when male and female both are singing together, it's always this female voice dominates a bit the male.
Really? My goodness.
Yes.
We should encourage equality, isn't it? I mean, we are talking about gender equality these days. Yeah. Yes. That, yeah, I think there she has an answer, yes.
It's a notes. Like female have different type of notes, and the female.
For example, suppose very correct. Could you introduce yourself?
I'm Rakhi from Gokte Institute of Technology, Belgaum.
No, but could you also elaborate what you said? Explain more.
If you have played a piano, this side will be the right side will be the softer, and right side is softer, and left side is little harsh. So notes are different.
By left and right, I'm sorry to interrupt you. By the left and right, are you speaking about a keyboard?
Keyboard.
Okay.
So this side, we usually get a female voice.
Okay.
And left side, we get a male voice. Notes are different.
That's right. So the notes are
also
different.
The frequency.
Now, so the notes are different is correct. That is an accurate way of saying it. Softer and harder, I don't know. I mean, it may. So the notes on the right are of higher frequency. If you were to, in fact, if you can do this experiment yourself. If you have a mechanism to record the so-called right side notes and the left side notes, and you record them and then see what you have recorded in an audio file, you will find that the notes on the right side vary faster and the notes on the left side vary more slowly. That is true. The frequency is different. So, notes, yes, so in music it's easier to understand this difference. So, it means that female voices are typically a little more higher frequency. So, in fact, you know, if you want even if you have males and females singing together and you want the whole song to sound harmonious, then you must have an octave separation between them. So, many of you who know music would understand the meaning of an octave. The same Saregama Pa. So, if it's an Indian piece, then Saregama Pa Da Ni. There are several sides. So, you know, you can have Saregama Pa Da Ni going 3 times, you know, on the scale. So, typically the male would be the lower octave and the female would be the higher octave. It has to be harmonious. In fact, there must also be a confluence of the two in terms of the relative positioning of the notes. So, why I am bringing all this out is, in all this, we need to think of the frequency of the sound that is being generated, right. So, females typically would work with higher octaves and males would work with lower octaves. Both of them are equally soft, both of them are equally beautiful, and both of them are equally melodious, right. So, now the important thing is that suppose you wish to distinguish between the male and the female component. What do you need? So, how does it translate into something actionable from a mathematics point of view? You should be able to recognize that this audio recording has both so-called low frequency content and so-called high frequency content. And then you must be able to distinguish the low frequency content and enhance it. And all this should be doable with a system, right? All this should be doable with a system. Now, when you think of doing all this, it looks very demanding, but actually it isn't really so demanding. So, let's look at this very simple example of an averaging system. What does it do? Now, we need to first ask some questions. You see, suppose you had a continuous time sine wave. How would you write it? So, a continuous time sine wave, x of the continuous variable t is time. Right, so we could write it something like A naught is the amplitude and cos omega naught t plus phi naught. This is a continuous time sine wave, isn't it? With amplitude A, angular frequency omega and phase phi. Now let us sample it at t equal to n ts. Ts is a sampling interval. Okay. So, now for example, if you are talking about audio, what would Ts be? What is a good value for Ts? If you are talking about audio, yes? I know, but that's what I am trying to see. You must only use only the things I have talked about so far, you know. Don't bring in, like there's this, yes. 1 upon 10. 1 upon 10th millisecond, is it enough for audio? Not for audio. That's okay for speech. 1 upon 40, yeah. So, 1 by 40th millisecond. Yes, 1 by 40 millisecond is a good value for TS, right. Now, that means you would get, when you did this, you would get x of n, which is A naught cos omega naught n ts plus phi naught. Is that right? This gives you the sequence x of n. And now you need to ask the question, is there a limit on how you could handle omega naught? In other words, up to what range of omega naught will you be able to distinguish this sequence? Or are there values of omega naught which would produce the same sequence? That's another way of asking the question. So, now let me ask you the question, are there values of omega naught which would produce the same sequence? Suppose I give you a particular omega naught and generate a sequence like this. Are there any other values of omega naught which will generate the same sequence? Well, I'll answer the question for you. Suppose you added any multiple of 2 pi. By Ts. Suppose you replaced omega naught by omega naught plus 2 pi by Ts times k. What would happen here? You would get A naught cos omega naught plus 2 pi by Ts times k into Tsn plus phi naught. Okay. But A naught, so if you simplify this, this can be seen to be A naught cos omega naught n Ts plus 2 pi Kn plus phi naught. Is that right? Now, adding any Kn are both integers, so adding any multiple of 2 pi to the cosine leaves it unchanged. And therefore, all these angular frequencies will produce the same sequence. Is that right? That means that we cannot distinguish. If you look at this sequence x of n, you cannot distinguish between the frequency omega naught and the frequency omega naught plus any multiple of 2 pi, or rather any multiple of 2 pi by Ts. Is that right? That is the angular frequency of sampling. So the frequency of sampling is 1 by Ts, and the angular frequency of sampling is 2 pi times that frequency. So 2 pi times 1 by Ts. So any multiple of the angular frequency of sampling leaves this sequence unchanged, which means that as far as if you are going to do anything with that sequence, you can only work with a restricted range of frequencies. What is that restricted range of frequencies? One region of 2 pi by Ts. In fact, not even one range, because if you take one region of 2 pi by Ts, so the distinguishable frequencies, you see, in fact, there's another problem. Cos omega naught etc. is the same. Cos alpha is equal to minus cos alpha, cos of minus alpha. Is that right? That's another problem. The cosine is again ambiguous in terms of the sign of the argument. The cos of alpha is cos of minus alpha. And because of that, in fact, now you're going to have an ambiguity on both sides of 0 also. You can think of it like that. That means actually you have only a range of half 2 pi by Ts to work with. That means you can only distinguish, we can only work with angular frequencies zero to pi by Ts. Is that right? Is that right? Because otherwise, if you take any frequency outside this range, it's going to appear to be a frequency, some other frequency. So it's going to look exactly how some other frequency looks. Right? You cannot distinguish. By looking at the samples, I cannot distinguish. That is the problem. Right? So that means if I am working with a discrete sequence, then I can only work with a finite range of frequencies. This range of frequencies is 0 to pi by Ts, or the other way of looking at it is, this is the angular frequencies, but if you look at the per cycles per second frequency, what would it be? It would be half of 1 by Ts. So as Rahul said, you cannot exceed half of the sampling rate in your sinusoid. The sinusoid, the sine wave, cannot exceed half the sampling rate in frequency for it to be distinguishable clearly. Now, if you now think of it like this. So now you have a sampling rate of 40 kilohertz. What does it mean? For 40 kilohertz means the maximum the maximum frequency admissible is half of 40 kilohertz, which is 20 kilohertz, and that's good, because you know that typically audio signals have frequencies that lie between 20 hertz and 20 kilohertz. Is that right? So this is good. If you are sampling at 40 kilohertz, you're doing well. Now so therefore, you see, now when we talk about a discrete system, it's always going to be dealing with a limited range of frequencies, limited range of sine wave frequencies. Now let's take the system that we started with, the averaging system. let's take the averaging system. And let's assume that to the averaging system we gave a sample sinusoid. So we have the 2-point average. Now we gave a sample, so we have obeyed that omega naught is between 0 and pi by ts, or if you want to say half of 2 pi by ts, you want to write it like that. Now take the averaging system. So you have y of n is half x of n plus x of n minus 1. And you have given the sequence x of n is a naught cos omega naught n ts plus phi naught. You have given this sample sine wave as the input. Now here is a think, pair, share exercise that all of us will do. This time we will take more time to do it. So all of you need to first solve this on your own. Please listen to the question. The question is, so exercise, obtain y of n here. Write it as a sinusoid. Identify the amplitude and phase change. Phase change, amplitude and phase change. How does the amplitude of the sine wave change and how does the phase of the sine wave change? This is the exercise that all of you will do. Now all of you will please spend 5 minutes in doing this on your own. So when you are doing it on your own, you must write it down, you must try to solve it, or maybe 3 minutes. Let's do one thing. Let's take only parts A and B. And all of you should take 3 minutes to try and solve parts A and B on your own. Don't consult your neighbor then. So let's do that first. You take only 3 minutes to solve parts A and B. And there you don't consult your neighbor. I'll tell you when to consult your neighbor. So in part B, you should be able to write it like a sine wave, just as you see a sine wave there with an amplitude and phase, and of course the frequency. In fact, the hint is that the sinusoid would have the same frequency. The output sinusoid would have the same frequency. Oh, now there's one point. Now when we say sine or for us, sine and cos mean the same thing. It's all sinusoid, right? Because the different change of phase would make a sine into a cos. So sine and cos are not really different. They're really all sinusoids. We use the word sinusoid. Is that right? So sinusoid, when you change, so a sine, when you change the phase, becomes a cosine. So sine, cosine are not fundamentally different. How many of us are individually done? Can you raise your hands? How many of us are individually done? None of us are individually done? Okay, let's take a little more time. Let's first make an individual attempt. I'll give you a hint. You need to use trigonometric identities. Let me give you a hint. So you can use the trigonometric identity cos, I'm writing it here. Cos C plus cos D is equal to what? Twice cosine something, isn't it? Well, now we can share. So you can share and improve your solution. That is, you can pair and improve your solution. So you can consult your neighbor and improve your solution. And we give you about 2 to 3 minutes for that. Is that right? So you can discuss it with your neighbor, with your partner, and improve upon your solution. And as you pair, that as you discuss with your neighbor, you must also try to answer part C. So when you are discussing with your neighbor, you must also attempt part C. Phase change. The part C says, identify the amplitude and the phase change, which the sine wave has undergone. Do we have any group which is ready with an answer? You're ready with an answer? Very good. So I'll invite, yes, you're also ready with an answer? Okay, so we'll invite Rahul and his partner to come and answer. Yes. And write down. Now all of you will pay attention to what Rahul is doing. And you can introduce yourselves.
Hello. Myself, Rahul Ingre. I'm faculty member in VJTI, Mumbai, in electrical engineering department.
Hello, I am Shraddha Suretkar from VJTI from computer department.
Okay, good. Oh, but you shouldn't have been together. That's cheating. I told you you shouldn't have computer and electrical sitting together. So now please separate after this.
Right,
Yes.
sure.
Yes. You can write down only the main steps. How many of you are done? How many of you have worked it out? How many groups you have? Very good. That's nice to know. All the other groups continue to work it out. Well, how many of you agree with him? No, I don't. Isn't it? There's a mistake. Okay, thank you, well attempted, but there is some, you have made mistakes in the substitution there. Would somebody like to improve? Any volunteer to come and improve the solution? Maybe you can, please come and improve the solution. Oh, well, all right. Okay. Maybe you could, anyway, you can write the main steps, right? So, because otherwise it will occupy a lot of time. Write down the main steps. Write big, please. Yes. Everybody can see. Now, you may wonder why we are going through all this. The reason why we are going through all this is not simply to convey the idea, it's also to convey a pedagogical practice. It's also to convey a way of teaching, right? It's not simply to convey the idea, it's also to convey a pedagogical practice. Very good. Excellent, yeah. Very true, yes. Yes. Very good. Could you use, let's use a different color perhaps. So we had colored chalk, yes. We had colored chalk somewhere, didn't we? Anyway, it doesn't matter. You could just use the white chalk itself and identify the change of amplitude and change of phase. Yeah, use the mic and explain why you introduce yourself and use the mic and explain the change of amplitude.
This is amplitude.
Speak into the mic.
Okay. And this is change of phase.
Change. Can you write that down? Okay, so this is a change of amplitude. So, so this is not. This is the amplitude, but which is
change. This is change.
This is this is the change of amplitude.
This is amplitude.
Yeah, very correct. What's your name?
Preetam Wani.
Preeta. Yeah.
Yes.
So this is the change of amplitude, and this is the change of phase. Is that right? Now, is that clear to everybody? Now, has anybody, how many of you were able to arrive at this? Can you raise your hands? Yeah, many of you were able to arrive. How many of you have not understood some steps here? Yes, you've not understood some steps here? Oh, okay. Everybody's understood all the steps? Yes? So you see there are two things that you observe here. The system has an interesting property. When you gave a sinusoid to it, it gives you a sinusoid of the same frequency. That's one thing, isn't it? Secondly, it changes the amplitude and the phase of the sinusoid in a particular way. Let's understand what change of amplitude and phase has occurred. So now, we'll hold that there. So we have the change of amplitude and phase. Now how has the change of amplitude and phase occurred? Let's sketch it. Let's sketch. So if you look at it, the amplitude change, let's first focus on the amplitude change. Cos omega naught into Ts by 2, right? Now remember, omega naught is always between 0 and pi by Ts. We agree that omega naught cannot be more than pi by Ts because it's undistinguishable then, right? So let us write omega naught Ts as omega naught divided by 1 by Ts. Right? So this is equal to omega naught Ts. So what is the physical interpretation? Omega naught divided by 1 by Ts is a normalized angular frequency. Omega naught into Ts is therefore a normalized angular frequency. And we will denote omega naught Ts by small omega. We'll denote it by small omega. It's the normalized angular frequency. So normalized angular frequency can only take values between 0 and pi. So omega must lie between 0 and pi. Is that right? So it's only between 0 and pi that the normalized angular frequency can lie. Is that right? Let us now sketch. So then this amplitude change would become cos omega by 2, isn't it? Becomes cos omega by 2. Let us sketch this cos omega by 2 as a function of omega between 0 and pi. How does it look? So it takes the value 1 at 0 cos omega by 2 and comes to this is cos omega by 2. This is how the amplitude changes. Now what is the physical interpretation? This is 0 hertz and this is, what is pi? Pi corresponds to 20 kilohertz, isn't it? If you are taking audio as an example, pi corresponds to 20 kilohertz. And of course 0 corresponds to 0. So So what are we saying? What does this system do? What does this 2-point average do? It enhances the lower frequencies and suppresses the higher frequencies. So it enhances the lower frequencies and suppresses the higher frequencies. Can you see that? The amplitude, so from the amplitude, suppose you're talking in terms of male and female voices, what would it do? What would the system do? It would enhance the male voices broadly and reduce the female amplitudes. Now I want you to work out another example. We'll come to the phase afterwards. I want you to work out another example and tell me what it does. So in fact, therefore, this system is also called a low pass filter. It's a very simple example of a low pass filter. So that now 2 words, filter. Filter is a term used for a system which changes the relative content of different sinusoidal frequencies. Right? So here this is a low pass filter because it passes or it allows the lower frequencies to go through with little more emphasis as compared to the higher frequencies. So it's called a low pass filter. Now I'm going to give you another system and I want you to analyze and tell me what that system would do on similar line. This time we'll take a little less time to do the analysis. So now similarly analyze this system. Now we have another system. Y of n is half x of n minus x of n minus 1. So it's a 2-point difference. So what you're doing is you're finding the difference between the current sample and the past sample. Right? You're taking a multiple of the difference between the current sample and the past sample. So I want you to find out what this system would do to a sine wave and sketch the amplitude change only. Yes. So first do it individually, take about 3 to 4 minutes to do it individually and then consult your neighbor. Don't consult your neighbor before you do it individually. So take 3 minutes and do it individually. Use the same line of reasoning. This time of course the line of reasoning would be cos C minus cos D. What would it be? Cos C minus cos D. What is the identity? Half, tell me, half cos. I'm sorry, yeah. Twice cos C plus D by 2 sine sine C plus D by 2 sine D minus C by 2. That's correct. So let's take 2 to 3 minutes to first solve it individually and then don't consult your neighbor until then. So take 3 minutes and solve it yourself. And just like I sketch the amplitude change as a function of small omega and then consult your neighbor. You can take help from your neighbor now. You can take help from your neighbor and improve upon what you're doing. You can use them as neighbors. Very good, you've done it very good. So I have one volunteer who's willing to. Oh, you're not a volunteer? What a pity. Why? Why not? The people who make a mistake on the blackboard do the greatest service to the class. Right? So if you make a mistake on the blackboard, you should be complimented for it. Isn't it? Oh, very good. That's good. So are you a volunteer then? Would you be a volunteer for solving on the blackboard? I think. Yes, why not? I think we should, yeah. So we have a volunteer. Professor Gandhi is going to volunteer now. So Professor Gandhi will volunteer to solve it on the board.
Yes, so we get yn is equal to a0 times.
Do write a bit big so everybody can see.
Minus 1 sine of omega 0 ts by 2 into cos of omega 0 ts n plus phi 0 minus omega 0 ts minus pi by 2. So this is change in amplitude.
Yes.
And this is change in phase.
Yes, that is almost correct. maybe
And
a small improvement. Yes, when you're talking about amplitude, amplitude must be non-negative.
yeah,
Right? So the so what is the change of amplitude? So modulus of sine omega. So that is the change of.
okay.
Yeah.
So it should
That
be
right?
mode
So,
of -1 sine.
that's correct. Now
And
here's
if
a
we
sketch for that. Yeah.
sketch this,
Sketch as a function of small omega. Yes.
so it will move like this.
Now, would you like to improve upon that? So since it's an amplitude, it must be non-negative.
Okay.
So yes.
So it will go upside.
You can erase and yeah. That is, yes. Very correct. How many of you get this? How many of you got this? Oh, that's very good. How many of you don't understand some step here? There's some step who didn't understand. Have we understood this? Very good. Now, very good. So now, what is your comment? What does this system do? It's a yes. What does the system do? Gender equality, isn't it? Initially we had yes. So initially the male voices were strengthened by xn plus xn minus 1 by 2. Now what is happening? The female voices are going to be strengthened by xn minus 1, xn minus 1 by 2. Isn't it? So this is called, what kind of a filter is this? It's a high pass filter because it enhances the higher frequencies and suppresses the lower frequencies. Is that right? So together these, one of them enhances the male voices initially, and now this would enhance the female voices in the audio, isn't it? Now, so now you understand, now you now you are beginning to see the role of going into a different domain, right? So now the same system, you could describe the system in the time domain. What is the description of the system in the time domain? Well, let's go back to that. So this is a time domain description of the system. This is a time domain description of the system. It describes what the system does in the natural domain. The sequence naturally is a function of time, so it describes what the system does in the natural domain. What does this do? What does this do? This is a frequency domain description of the system. This is a frequency domain description. So it tells you what the system does to different frequencies of sinusoids that could be fed to it. So it's a frequency domain description of the system. Now we are going to see how we can go from a time domain to a frequency domain description. Of course, you did it here by brute force. What do you mean by brute force? You fed a sine wave into the system and saw what came out. Right? Now you can't do that every time. Right? You must have a better way of doing this. You must have a better way of moving from the time domain to the frequency domain, and then also coming back from the frequency domain to the time domain. Right? You must have a better way of doing it. Now, to have that better way of doing it, let us see something more about this time domain system. Let's come to the time domain description and let's find a better way of. Now, to move between the two domains, the time domain and the frequency domain, we are going to use what is called a transform. So what is a transform? A transform is a mapping of domains or paradigms. So in fact, you see, you started with sequences. Sequences are mappings. They are mappings. What kind of mappings are they? Mappings from script Z to script C. From the set of integers to set of complex numbers. What are systems? Systems are mappings from sequences to sequences. So it's one layer higher. Mappings from input sequence to output sequence. Right? Now we come to one layer higher. So what is a transform? A transform is a mapping again. But now this is one layer. So what is a mapping? It's a mapping from one domain or one paradigm to another paradigm. So it carries the sequences and the systems from one domain or one paradigm to another paradigm. It's a mapping from one paradigm to another paradigm. What do you mean by the word paradigm? What is the meaning of the word paradigm? Yes? Representation. Paradigm literally means, what is the literal meaning of paradigm? World view, the way you look at the world. That's called paradigm. Or domain, that's another way of saying it. So paradigm means the world view, the way you look at that means the way you're looking at signals and systems all together. That's the paradigm. You could say time domain paradigm and frequency domain paradigm, or time domain description, frequency domain description, isn't it? So now we are going to make this transformation from the time domain paradigm to the frequency. How will we do that? To do this, we need to first employ an intermediate step. We need to discuss what is called, see, what is that one sequence which would tell you everything about the system? That is what we need to see. So if I took this system, for that matter, these systems are very special, the kinds of systems that we are looking at. Now let's take any sequence, forget about the system. Let's take any sequence x of n. Now one way of writing a sequence is to use what is called the arrow notation. So for example, I could use an arrow notation. This denotes the value of n. So you're saying at n equal to 0, the sequence takes, let's say, the value 5. And then you write the numbers around it. So let's say -8 or 6, whatever. So now, how would we read this? We would read it by saying x of 0 is equal to 5, x of 1 is equal to 7, x of 2 is equal to -2, x of 3 is equal to 8, and so on. And x of -1 is equal to -8, and x of -2 is equal to 6, and so on and so forth. This is called the arrow notation. Of course, the arrow notation is useful, particularly when the sequence is of finite length. So for example, suppose this sequence had no more non-zero samples. So all the samples before this were 0 and all the samples after this were 0, then this arrow notation is a convenient way of writing a finite length sequence. Let's take the finite length sequence as an example here. Now, can we take a very primordial sequence? So we have a very primordial sequence called delta n. We call it the unit impulse sequence. And this sequence is 1 for n equal to 0 and 0 otherwise. Right? So it's 1 when n is equal to 0 and 0 everywhere else. Can we think of this? Let's take this sequence to be a finite length sequence. So it's a sequence which goes only from -2 to, this was 0 here. So -2 to +3, and it's 0 outside that interval. Now, can you write this sequence as a combination of delta n's? Yes, indeed you can. How will you do it? You would say x of n, if this is x of n, x of n, can you tell me? It would be, well, 5 times delta n plus 7 times delta of n minus 1. What would delta of n minus 1 be? Delta of n minus 1 would be a sequence which is 1 at n minus 1 equal to 0, which means n equal to 1 and 0 everywhere else. Is that right? So delta of n minus 1 is again a primordial sequence which takes the value 1 at n equal to 1 and 0 else. So 7 times delta n minus 1 minus 2 times delta n minus 2 plus 8 times delta n minus 3, and then plus, of course, minus 8 times delta n plus 1 or minus of minus 1, and plus 6 times delta n plus 2. You agree with me? So you see the pattern, right? So you could express any sequence as a combination of this primordial sequence called the unit impulse sequence. Can we write a general expression for this? Yes. We could write. Yes, I'm sorry. Yes. Where, which plus? Yes. Yes. Oh, I have added several primordial sequences. So what I'm doing here is I'm adding, so it's like adding every point, one point by point to the sequence. Each point in the sequence can be thought of as a primordial sequence. It's really a shifted and scaled version of the unit impulse sequence. Is that right? So any sequence is really a combination of shifted and scaled versions of the primordial unit impulse sequence. So what is the more general expression? X of n is summation k going from minus to plus infinity, x of k delta n minus k. Is that right? This is a way of writing this in general. So the sequence delta n, this unit impulse sequence, allows you to write down any sequence as a linear combination of this primordial sequence shifted and appropriately scaled. And what is the scaling factor? The value of the sequence at individual points, x of k. Is that right? Now this is a very important principle. And now let's assume that, so you see, why are we observing this feature of the unit impulse sequence? Because this will enable us to characterize the action of any systems of a particular kind. Now the two systems that we saw so far, the so-called low-pass filter and the so-called high-pass filter, both have certain important properties. I'm not going into those properties right now, but both of them can be completely characterized by what they do to this unit impulse sequence. So let us see. So let's take that unit impulse sequence and apply it to this system. In fact, let's do something more general. Let's take the unit impulse sequence. Okay, let's do the more particular thing first. Let's apply it to the system. Y of n is x of n plus x of n minus 1. Is that right? And what would we get? Of course, we would get half of delta n plus delta n minus 1. Is that right? Now this is called a unit impulse response of the system. This is called a unit impulse response of the system. Yes. Delta n is now used as the input to this system, right? And I am finding out what the system would produce. This is a system. System was a 2-point average. So I found out what the system would produce. It would produce this sequence. In fact, you can sketch this sequence. How will this sequence, what is this sequence? Let us call it, in fact, let's give it a name. We'll call it h of n. The unit impulse response is often written as h of n. So how can you write h of n in arrow notation? H of n, how will we write in arrow notation? It will look like this, isn't it? You agree with me? This is how h of n will look in arrow notation. It's half at n equal to 0 and half at n equal to 1 and 0 elsewhere. Is that correct? You all agree with me? Now, let us look at what this, so you see, now let's do something interesting. Let's go to a sinusoid. Oh, sorry, let me not erase this. Let me keep it. Let's keep this. Let me bring that down. Now, let's take a sinusoid. And let's take a sinusoid as a combination of two complex numbers. There's a reason for that. You see, if you have a sinusoid, if you take a discrete sinusoid, so you have a naught cos small omega n plus phi naught, isn't it? Omega, as you remember, was capital omega by 1 by ts. isn't it? So this is a discrete sinusoid. Now the discrete sinusoid can be written as a combination of two complex numbers rotating in opposite directions. So we could write it as half a naught e raised to the power j omega n by plus phi naught plus half a naught e raised to the power j minus omega n minus phi naught. Is that right? So what is the physical interpretation? You have two complex numbers rotating in opposite directions. If you think of omega now as an angular frequency and n is the time index, you're looking at two sine. Can you visualize that? There are two sine waves, there are two complex numbers which are rotating. One of them is rotating with a positive angular velocity omega, the other one is rotating with a negative angular velocity. And they come together to form a sine wave. In fact, any sinusoid is really a combination of two oppositely rotating complex numbers. Is that right? Can you see that from here? Now let's focus our attention on any one of these. Let's focus our attention on any one of these. Let us now we bring up linear algebra, right? So here we are going to employ, let us now recall our notion of dot product. Is that right? So let us recall our notion of the dot product. What is a dot product? So in fact, let me again bring this down and forget about this, only keep this here. See, now we want to build up the idea of a dot product. Of course, I know that you are familiar with it, but let's again sort of build it up from a certain perspective. What is a good way to represent two-dimensional vectors with two coordinates? So if you have, now you see, the thought that I am trying to bring out here is that a sequence is like a vector. So xn is like a vector. In fact, xn is like an infinite dimensional vector. A sequence is an infinite dimensional vector. What is the index of the dimension? N. So each n index is a different dimension. So if you have two sequences, x1 of n and x2 of n, how would you write dot product between these two vectors? Very simple. You multiply the corresponding coordinates and add. So let's do that. So in fact, you know that the dot, I think you may have been exposed to dot product. So the dot product, the more general term for the dot product is inner product. So the inner product is written like this. And what would it be? It would be summation n going from minus to plus infinity, x1 n, x2 n, but then we have to be cautious. We said that we will also want to allow complex numbers here. Now if you took the dot product of a vector with itself, what would you want out of that dot product? What would you want out of that dot product? Yes? Try and minimize the use of terminology. What would you want out of that dot product? The length, yeah. So you would want, in some sense, to get the square of the length or square. It should, but what properties should that length have? It must be non-negative. When will it be 0? Only the vector itself is 0. Not only that, if it is not 0, the quantity should be strictly positive. Now, will this definition allow that to happen? In fact, suppose, let me give you an example. Suppose x of n is, by arrow notation, 1 and j. Now, I use j to denote square root of minus 1, right? So, if I have this sequence, and in arrow notation, I have a finite length sequence which takes the value 1 at n equal to 0 and j at n equal to 1. And if I did this, if I use this idea of the dot product, what would be the so-called dot product here of xn with itself? 0. So that's not good, isn't it? Because you have a non-zero vector which gives you a 0 dot product with itself. You don't want that. So should we make a little change in our definition of the dot product so that this doesn't happen? Well, a very small change will do the job. What is that small change? You take a complex conjugate of the second argument. Is that right? So when you're dealing with complex sequences, you would make this small change in the dot product. You would take the complex conjugate of the second argument. Is that right? And if you do that, now what will the dot product be? If you take the dot product of the vector with itself, 1 with 1 and 1 with 1. So the dot product would be 2. And that would, in fact, you can see in general that if you took the dot product of xn with itself, If you took xn with xn, and if you use this definition, what would it give you? Xn dot product with itself is summation n going from minus to plus infinity mod xn squared. Is that right? Xn into xn complex conjugate, so mod xn squared. So this would definitely be non-negative, and in fact it would be 0 only if and only if xn is 0 for every n. So non-zero vector would give you a positive dot product with itself, and a 0 vector would give you a 0 dot product. So this in fact is called the 2 norm. It's the L2 norm, small. It's the 2 norm of the vector. Formal in linear algebra terms. Yes. What is the physical interpretation? The physical interpretation is like a magnitude squared that you associate with the vector. Now let's use this idea of the dot product. And let's take the dot product of this impulse response, unit impulse response, with one of those rotating complex numbers. So let's take the impulse, let's take the dot product of, let's take any one of those rotating complex numbers. So let's take the positively rotating one, for example. The positively rotating one is half a naught e raised to the power j omega n plus phi naught. And let's take the dot product of this with the impulse response. What would it give you? Right? So, please calculate. In fact, let's make the matter even simpler. Let's not bother about all this half a naught and phi naught. Let's simply take this rotating complex number. E raised to the power j omega n is enough to make it rotate, isn't it? E raised to the power j omega n is enough to make it rotate. You don't, amplitude and phase is okay. That's so. Let's take this dot product. What would that dot product be? Well, half e raised to the power j omega 0 plus half e raised to the power. In fact, let's reverse the sign. So let's take hn dot product of hn with e raised to the power j omega. Right. So let's inverse the order of the argument. So e raised to the power minus j omega 0 plus half e raised to the power minus j omega into 1, isn't it? So let's rewrite this. So this would be half 1 plus e raised to the power minus j omega. Is that right? Now let's write this. It's a complex number. It's a function of small omega. Is that right? It's a function of small omega. So let us write this in magnitude. Let's write in polar form. What is the polar form of this? Half into 2. Well, to write in polar form, you could take the magnitude, but it will be easier to write it like this. Take e raised to the power minus j omega by 2 common, and that leaves you with 2 cos omega by 2 inside, isn't it? E raised to the power minus j omega by 2 plus e raised to the power plus j omega by 2. You all agree with me? This is the polar form, or this is the simplification. So therefore, the dot product would give you e raised to the power minus j omega by 2 cos omega by 2. Now, does this sound familiar? Does this ring a bell somewhere? So, you've taken a dot product of the impulse response with this rotating complex number e raised to the power j omega n, right? And you get this e raised to the power minus. Now, go back to your change of amplitude and change of phase. See, can you link it to that? Yes, you see something similar here? So, in fact, this is the change of amplitude. Is that right? This is the change of amplitude. And where is the change of phase reflected? Here. What is the change of phase there? Look at it. What is the change of phase in that system? Yes, minus omega naught. So, in that system, the change of amplitude was the change of amplitude in that system was cos omega by 2, isn't it? And what was the change of phase? What was the change of phase? Minus omega by 2, that's correct. And that's exactly what you see here. Is that right? The angle of this complex number reflects the change of phase. And the magnitude of the complex number reflects the change of magnitude. Now this all starts making a lot of sense, doesn't it? You've taken the dot product or the inner product of the impulse response with a rotating complex number. The rotating complex number generates a sinusoid. Two of them rotating in opposite directions generate a sinusoid. When you took the inner product of the impulse response with a rotating complex number, the magnitude and phase of that inner product reflects the change of amplitude and the change of phase in a sinusoid, which would be given as an input to the system. Is that right? You see what's happening? Now, this process of finding the inner product is actually a transform. In fact, what we just did by finding the inner product is the discrete time Fourier transform. So this, what we did there, let's go back there. When we took the inner product, h of n with e raised to the power j omega n. This is in fact the discrete time Fourier transform or DTFT. It's also called the DTFT of Hn. The discrete time Fourier transform of the sequence Hn. Yes. Here Hn was the impulse response. But now we don't have to confine ourselves to the impulse response. Hn could have been any sequence really. And you could take an inner product of a sequence with this rotating complex number. Now what is the physical interpretation? When you take an inner product, what are you really doing? Now many of you might also be aware of physics. When you take a dot product of one vector with another, what does it give you? If you take a dot product of a vector with a unit vector in a certain direction, it gives you the projection of that vector in that direction, or it gives you the component of that vector in that. Now that also makes sense here. When you take the product, when you take the dot product of the impulse response with a rotating complex number, it gives you the projection of the impulse response upon that rotating complex number. Which means it tells you what it does to that rotating complex number, right? In some sense, what the system does to that rotating complex number. And the other way of looking at it is, if I took the dot product of any sequence with a rotating complex number, it tells us what component of that rotating complex number is present in the sequence Xn. How much of what component of that rotating complex number is present in the sequence Xn. That's why it's called the discrete time Fourier transform. It tells you the content of that rotating complex number present in the sequence Xn. Right? And now we'll see. So in fact, you saw how so now you see how the discrete time Fourier transform allows you to change the paradigm, change the way you're looking at the system. So tomorrow we'll build further on this. We'll understand how the discrete time Fourier transform gives you a full change of paradigm. That is, what you're doing in the time domain can be described equivalently as what you're doing in the frequency domain. And then we'll see more about the Fourier transform, and depending on the time, we'll also look at other transforms. Is that right?